Okay, so in the last couple of videos, we've been talking about the first part of this unit, which has to do with circular motion basics. In this video, we're going to start talking about the next section of this unit, which has to do with centripetal force and acceleration. Okay, and so before we get into that, I want you to look at this question and see if you can answer this question. Okay, and the question is it possible for an object to move at constant speed and still be accelerating? Is it possible for an object to move at constant speed and still have an acceleration? And the hint I'm going to give you is think back to what is the actual definition of acceleration. Okay, so try and answer that question now. Okay, the answer to this question is yes, it is possible for an object to move at a constant speed and still have an acceleration. Acceleration does not mean speeding up or slowing down, although it can mean that. Okay, the actual definition of acceleration is the rate at which an object's velocity changes. Meaning, by definition, if an object has a changing velocity, it must be accelerating. Okay, now, velocity is a vector. Okay, velocity has basically two parts to it. Okay, like any vector, it has magnitude, and the magnitude of velocity we call speed, but it also has direction. And if either of those two things change over time, then you have acceleration. Okay, so up till now, we've seen, if an object starts moving faster or slower, it's accelerating. That is, if the magnitude of the velocity changes, but we've never considered what if the direction of the velocity changes. Okay, well, in that case, by definition, we would also have to have some type of acceleration. So it is possible for an object to move at a constant speed and still be accelerating as long as the direction part is changing over time. Okay, so keeping that concept in mind, let's talk about how that relates to circular motion. Let's see, going back, this is just a review of some concepts we've talked about before. The definition of acceleration, of course. I do want to remind you about Newton's first law. Here's what Newton's first law says, the way we stated it in class last semester. An object at rest will remain at rest, and an object in motion will remain in motion at constant speed along a straight line unless acted upon by a net force. Notice that constant speed in a straight line is the same thing as constant velocity, because remember, if an object's velocity changes, that means either the speed has to change or the direction has to change. So by saying constant speed in a straight line, we're basically saying that the magnitude of velocity is not changing and the direction of velocity is also not changing. Okay, and so such an object is going to remain in that type of motion unless acted upon by a net force. And then we have everybody's favorite equation, F net equals ma, Newton's second law. Okay, so for an object moving at constant speed along a straight line, that object must experience no acceleration. Okay, so there's three ways an object can be experiencing acceleration, as we talked about before. Either speeding up, slowing down, or changing direction. And so since this unit is about circular motion, you can probably guess where this is going. An object moving in circular motion is constantly changing direction because it's not moving in a straight line. And so that means an object moving in circular motion has to have acceleration. Okay, so for an object moving in what's called uniform circular motion, the object's velocity is continually changing at every moment in time. Really, any object moving in any type of circular motion is accelerating because the direction of the velocity is changing. When we talk about uniform circular motion, that basically refers to situations where angular velocity is constant. Okay, and so we are going to, let me just underline this, uniform circular motion. We're basically going to only assume in problems that omega, the angular velocity, is constant. In AP Physics and some other college-level physics classes, you do situations with angular acceleration, and then you have to deal with, objects accelerating as they move in circular motion. We're not going to do any of that. And all the problems we're going to do, we're going to assume that the angular velocity is constant, at least constant in magnitude, I should say. And so we're going to make that restriction in IB physics, at least in SL. It has that restriction. Okay, so as we've been talking about, any object with a changing velocity is by definition experiencing an acceleration. That acceleration in the context of circular motion has a specific name. Okay, the acceleration required for an object to move in circular motion, to move in a circular path, is called centripetal acceleration. Okay, so this word right here, centripetal. Okay, centripetal. Okay, so that is the acceleration that is required for an object to move in circular motion because its direction is changing. Okay, so make sure you add that word to your notes. Okay, I do want to come back and look at some simulations in just a few minutes, but first I want to talk about something related to direction. Okay, so as we're talking about circular motion, it becomes kind of inconvenient to only be able to use words like up, down, left, or right, because an object in circular motion, its direction is constantly changing. Okay, and so we're going to introduce two new terms to describe direction in the context of circular motion. And the two terms we're going to introduce are radial and tangential. Okay, radial comes from the word radius, meaning motion either towards or away from the center of the circle, along the radius of the circle. Okay, so towards the center or away from the center, that is what we call the radial direction. Okay, the tangential direction, the word tangential comes from tangent, which we've seen before. Tangential motion means motion along the outside of the circle. Okay, and so I'm going to show you some pictures of what that looks like, and then I'm going to show you some simulations. Okay, so this is basically showing you a circle. The red arrows, notice if an object is moving in a circle, the velocity is always changing. So these red arrows might represent the velocity vectors of an object in circular motion. And notice that the direction of the velocity is always changing. But even though the direction is always changing, it's always what we can describe as tangential, meaning always pointed along the outside of the circle, tangent to the circle at every location in space. Okay, these blue arrows we could describe as the radial direction. In this case, they're both going out from the center of the circle, and so I would say they are both radially outward. Okay, they could be drawn going towards the center, and then I would describe the direction as radially inward. So radial and tangential are just two words we use to describe direction in the context of circular motion. And that word tangent, we've already seen that before earlier in this unit. Okay, so before I come back to centripetal acceleration, let's take a look at some simulations. And so I think this is the simulation I want to look at. Okay, so what we have here, as the simulation loads, is two bugs on a wheel that is free to rotate. Okay, so we have a ladybug and we have a beetle. Okay, and what I can do is I can spin the wheel. And you can see how the angular displacement is changing over time down here. You can see the angular velocity down here in the bottom left. For some reason, it's in degrees per second. So this angular velocity is 84.75 degrees per second. Of course, if I wanted to, I could write that as radians per second. But this has some angular velocity. Okay, now I am going to show you a green arrow, and this green arrow represents the velocity vector of this ladybug. Okay, so here you can see this little green arrow. Okay, and notice that the direction of the green arrow is changing as a function of time. Okay, the length is not changing, but the direction is. Okay, indicating that acceleration we talked about before. If I increase the angular velocity, I'm going to increase the length of that green arrow, which represents the linear velocity, or what we also call the tangential velocity. The reason that the green arrow is now longer is very simple to understand. If you just think of the equation v equals r times omega, it should be clear that if I increase omega, I'm also going to increase v. And you can also tell by looking at the equation that if I increase the radius, that would also increase v. Okay, so here I'm going to put the beetle farther out from the center, and you can see that the velocity of the beetle is bigger than the velocity of the ladybug. Even though they have the same angular velocity, the beetle has a greater linear velocity because it's, the radius is bigger, it's farther from the center. Okay, now what I'm going to do is I'm going to show you the acceleration vector. Okay, pay close attention to this red arrow, which represents the acceleration vector for these objects. Now I'm going to take off the beetle actually. Look at the direction. Okay, and so notice that unlike the velocity vector, which was always tangential, the acceleration vector is what we call radial. Okay, and specifically, notice that that arrow is always pointed towards the center of the circle. And so I would describe the direction of this pink arrow here that represents the acceleration. I would describe that as radially inward. Okay, it's definitely radial, and it's inward, meaning in towards the center of the circle. Okay, and so this pink arrow, this acceleration, this is what I've been talking about over the past few minutes. Okay, so this acceleration has a name. Okay, and this is what we call centripetal acceleration. Okay, and so this pink arrow again represents the centripetal acceleration of the ladybug. And that's an acceleration not making the ladybug move faster or slower, but just changing the direction of the ladybug's velocity. Okay, so let's talk more about the centripetal acceleration. Now, there is an equation for centripetal acceleration that we'll see in just a second. Before I talk about that, I want you to know what centripetal means. Okay, so this centripetal acceleration is called centripetal because the word centripetal means center seeking. Okay, you might have noticed that the direction of that acceleration is always radially inward. Okay, that's why it's center seeking. Oops. Okay, so the name itself tells you the direction of the acceleration. Centripetal acceleration, center-seeking acceleration, always towards the center of the circle. Now, generally speaking, the magnitude of the centripetal acceleration depends on the speed of the object, how fast it's moving, and the radius of the circle. Okay, so here is the equation. We write AC for centripetal acceleration. And in terms of linear velocity or linear speed, that equation is v squared divided by r, where v is the speed of the object, that is the magnitude of the velocity of the object, and r is the radius of the circle. Now, let's say I ask you what are the units. Okay, so I don't know if we've talked about this before, but you can always figure out what the units of something are based off of the equation. And the way you do that is you take the equation and you plug the units of each quantity into the equation. So for example, what are the units for v? Well, we know that v has units of meters per second. We've been working with that all year. And the units of radius, just like any distance, if we stick with SI units, that is in meters. So let's say I want to know what are the units of centripetal acceleration. Well, this is v squared, so if I plug the unit into the equation, I get meters per second, all of that squared, and then divide by radius, and the unit for radius is meters. Okay, so meters per second, if I square that, I get meters squared, divide by seconds squared, and then I'm still dividing by meters, so there's also meters down here. Now notice one of the meters cancels, because meters squared divided by meters, one of that cancels. And so I find that the units of centripetal acceleration are meters divided by seconds squared, or in IB notation, meters per second squared. So centripetal acceleration has the same units as regular acceleration, and you probably could have guessed that on your own. But I wanted you to understand how to approach that type of problem, because sometimes you're asked to figure out what are the units for a given quantity, and you might not know immediately, but you can always figure it out as long as you have the equation. Okay, and so the equation for centripetal acceleration is v squared over r, but that same equation can be written in terms of angular velocity, because we know that v equals r times omega. Okay, we know that from the last video. Okay, so let me erase some of this and I'll show you how that can be derived. Now, which equation you use honestly just depends on what you're given. If you're given v, then you would use the equation with v. And if you're given omega, you would use the equation with omega. Okay, so because v equals r times omega, and I know centripetal acceleration is v squared over r, if I plug r times omega in for v squared, that would give me r times omega squared divided by r, and I would get r squared divided by r, which is just r, and then I would get omega squared. Okay, and so really I have two equations for centripetal acceleration, and the one that I would use, again, would just depend on what I'm given in the problem. Okay, so pause there and make sure you add that to your notes. Okay, so let's do some examples. Let's see. This is basically just showing you the equation again. It's showing you how the centripetal acceleration is towards the center of the circle, while the velocity is tangential to the circle. This is not necessary to show exactly, but if you're interested in understanding like why towards the center of the circle, take a look at this picture. Okay, so here you can see, I guess this is like a car going around in a circle or something. So let's say it has an initial velocity u and a final velocity v. Okay, then it's going around in a circle. The initial velocity is u, the final velocity is v. By definition, acceleration is the change in velocity over time, and change in velocity is final velocity minus initial velocity. Okay, and so if you do v minus u over time, look at the direction of v minus u. V minus u, if you think of in terms of vector addition, is basically the same as v plus negative u. And what you see right here in this box is basically just the tip-to-tail method by adding v plus negative u. Okay, so v plus negative u gives you an arrow that's going straight down, which in this case is going straight towards the center of the circle. And so this is just like a little quick way to visualize like why is the direction of the acceleration towards the center of the circle. That's just to kind of convince you that it is. Okay, so we're just going to do a few quick examples with calculations involving centripetal acceleration, and then we will move on from there. Okay, so example 1 says a runner moves around a curved road with a speed of 9 meters per second. The curve of the road has a radius of 12 meters. Calculate the centripetal acceleration of the runner. Well, centripetal acceleration is v squared over r. And so that would just be 9 squared divided by the radius, which is 12. Okay, and so I'm going to my calculator. 9 squared is 81, and 81 divided by 12 is 6.75, which if I wanted to round that to maybe like 6.8 meters per second squared, I can do that. Okay, so very basic calculation involving centripetal acceleration. Pause there if you need to look at that. Okay, example 2. It says a pilot can withstand 10 times the acceleration due to gravity. That is, they can withstand 10 Gs if he is wearing a special tight-fitting G suit designed to keep the blood from rushing to his brain. Okay, and 1 G, remember G is the acceleration due to gravity. The value we use on Earth is approximately 10 meters per second squared. It's really like 9.8 meters per second squared, but let's say 10 meters per second squared. And it says an 85 kilogram pilot is traveling at 1200 meters per second. He makes a circle with 10 g's of acceleration. What is the radius of the smallest circle in which the plane can turn around? Okay, so we know centripetal acceleration is v squared over r. And the reason it says the smallest circle is if you look at the equation, the bigger the circle, the smaller the centripetal acceleration is going to be. Okay, now he's going to pass out if AC, he's going to pass out if AC is greater than 10 g. That's what it says in the problem. Okay, and so we know a big radius is okay, but at some point if the radius is too small, then the acceleration is going to pass this threshold and he's going to pass out, okay, which is bad. Okay, so he will be okay as long as the centripetal acceleration is less than or equal to 10 g. Okay, so we can find that threshold radius by setting this equal. And so if we want the centripetal acceleration to equal 10 g, that would be 10 times 10 meters per second squared. And we know v is 1200, so it's 1200 squared. Then we can find r, where r is the minimum radius of the circle. Okay, and so if I rearrange this using algebra, I get r equals 1200 squared divided by 100, because 10 times 10 is 100. So 1200 squared divided by 100 is 14,400 meters. Okay, and any circle smaller than that, the guy's going to pass out, and that's bad. Okay, so again, a simple calculation involving centripetal acceleration. Pause there if you need to look at that some more. Okay, example 3. Okay, this one is a little trickier. So example 3 says, a boy swings a ball on a 1.5 meter long string at a frequency of 3 hertz. Calculate the centripetal acceleration acting on the ball. Okay, so this one is tricky because you're probably looking at your equations and you're thinking, okay, I've got this equation and I've got this equation, r omega squared, for centripetal acceleration. It doesn't say anything about frequency, right? Okay, and so this is where definitions are important. What does 3 hertz mean? What is a hertz? Okay, well, hertz is the unit of frequency, and when we say 3 hertz, by the definition of frequency, that is the number of rotations or revolutions an object makes per second. So 3 hertz is the same as 3 revolutions per second, which, if you think about it, 3 revolutions per second is angular velocity. It's not angular velocity in the correct SI units, but 3 revolutions per second is omega. Okay, it's just not in the correct units. And so if you think of it like that, based off of the definition, 3 revolutions per second, 3 rev per second, can be converted to omega in radians per second, because we know that 1 revolution is 2 pi radians. Okay, and so that would be 6 pi radians per second, which means that when they give us the frequency, they also give us the angular velocity. So 6 times pi is about 18.8 radians per second. And now if we have omega and we have the radius, which we do because we're given how long the string is, we know which equation to use because obviously now we have to use the equation that has omega. Okay, so the centripetal acceleration would be 1.5 times 18.8 squared. So 18.8 squared times 1.5 is approximately 530 meters per second squared. That is the answer to example 3. Okay, so pause there if you need to look at it some more. Okay, so let's see. The last thing I want to talk about, just really quickly, here, this is just a summary of the things we've been talking about. Okay, so look at that, and if you want to add this to your notes, you can, but most of the things we've talked about. Let's say, hypothetically speaking, you're driving along, and you know, when you're getting into your car, you put your plate of Pop-Tarts down on the top of the car, and you get inside the car and you forget the plate on top of your car. What happens if you're driving along and you take a sharp turn to the right? Okay, so imagine those Pop-Tarts. If you're driving in your car and you take the wheel and you swerve to the right, what's going to happen to the Pop-Tarts? Well, basically what's going to happen is the Pop-Tarts are going to keep moving in a straight line because of Newton's first law. If there's no force, a net force acting on the Pop-Tarts, your car is going to move in circular motion, but the Pop-Tarts are going to keep moving in a straight line. And so what that means is the worst case scenario is they're going to fly off the car. The best case scenario is if the car is moving in a circle and the Pop-Tarts keep trying to move in a straight line, what's going to happen is the Pop-Tarts are actually going to move towards like the left side of the car. Okay, and you also might have experienced a less extreme example of this if you've ever been in the car with somebody. If they swerve to the left, if you're in the passenger side, you feel pushed to the right. Okay, and likewise, if they swerve the wheel to the right, you feel pushed towards the left. Okay, towards the center of the car. Okay, and so what you're experiencing there is your body keeps trying to move in a straight line, whereas the car is actually moving around you in circular motion. And so that feeling that you feel like there's something pushing you towards the outside of the circle is not really a force. What you're really experiencing there is just inertia from Newton's first law. Okay, so that's just like a little concept thing. Okay, so we are going to come back to this in the next video. I think we're going to go ahead and stop it here. In the next video, we've talked about centripetal acceleration, but the main part of this section of the unit is about centripetal force, so we will get into the main part of the unit in the next video. Okay, and we will also do this type of example either in the next video or class. As always, please let me know if you have any questions, and I'll see you guys in the next video.